stable systems. If the poles are on RHS, then this type of diagrams will come, and those are unstable systems. Okay, those are unstable systems. Now I will go from the beginning. These are the terminologies. These are the terminologies we are going to look at. What is stability, transient response, steady state error, and then robustness, disturbance, rejection. And here what I have shown you is BIBO stable. BIBO stable, this is PDF, I don't have the coloring. Okay. BIBO stable means finite, bounded means it is finite. Bounded means it is finite. Okay. Bounded means it is finite. And then if input is finite, output also finite. Okay, it is not becoming infinite, then system is said to be stable. In the diagrams, you can see these three waveforms. These three waveforms in the diagram, amplitude is going on increasing. At t approaches infinity, amplitude also going to infinity. Okay, those three diagrams are unstable system. These three diagrams are unstable system. This type of diagrams will come when poles are on RHS. Poles are on RHS. When poles are on imaginary axis, the waveform will be a constant amplitude. You can see this sinusoidal waveform and the step signal. It is a constant amplitude. And if the pole is here, this is another type of waveform. And all these three waveforms, system is marginally stable, oscillatory. If poles are on imaginary axis, system is said to be oscillatory, marginally stable system. Marginally stable system. Okay. And if the poles are on LHS, you can see in this diagram, the other three diagrams, amplitude is decreasing. Other three diagrams, amplitude is decreasing. In those cases, poles are on LHS. And the amplitude goes on decreasing if poles are on LHS. Those are called stable system. Okay, these three diagrams are stable system. The right side three diagrams are unstable system. Amplitude is increasing, going to infinity, unstable system. And oscillator means constant amplitude. Marginally stable system. Okay. BIBO stable means this three, left side, this three stable, BIBO stable. It is a finite. Amplitude is finite when t approaches infinity. That is BIBO stable. We have seen what is stability. Now coming to transient response, steady state response. In underdamped system, we have seen second order underdamped system. This is the graph. Graph will go above the dotted line. Then it will decrease, will have some fluctuations. After that, will settle down with some error. This error is called steady state error. And up to the oscillations, it is called transient response. When it is oscillating with respect to final value, 3 or 5% is allowed, 2 or 5% is allowed. Okay. And those is said to be reaching the steady state. And this is steady state response. And in the transient response, we will calculate rise time, peak time, and then peak overshoot, delay time and all. At the settling period, we will calculate the settling time. Okay. All these are the terminologies. Settling error. Why I am going to this? You have transient response and you have steady state error. Which is at t approaches infinite, what is the minimum error for the output without reaching the final steady state value. Final steady state value is this dotted line, input reference or dotted line, input signal or reference signal or dotted line, one and the same. Output is this thick diagram. It should reach the input value, that constant horizontal line, that is our intention. Whatever the difference with respect to the constant line, that is called error, steady state error. Okay. And we have seen those terminologies. And next we are going with disturbance, rejection and sensitivity. So you can see here, by some external disturbances, ESS can be caused because of external disturbances, and it can track, can a system track the reference input despite of external disturbances? May be possible. Okay, and controllers, compensators we are using for that purpose. Denial of service attacks. Okay, service attacks means if a system is giving or satisfying a purpose, that service to be offered. Okay, that cannot be denied. If a system is designed for some purpose, it has to fulfill that purpose. It cannot deny the purpose. Okay, but what are the other disturbances occurring? It should be able to tolerate and manage to give the desired output. So that is the disturbance rejection. Sensitivity means relative change in output divided by relative change of the system parameter. System parameter means internally the system will have some design problems. Okay, for example, if I say a resistor, 1 kilo ohm resistor, but if you practically measure the resistor value, it may not be exactly 1 kilo ohm. It may be 1.1 kilo ohm or 0.98 kilo ohm, like that. That is manufacturer defect. Okay, and that is the system parameters or non-linearities in the design of the resistor. Non-linearities in the design of the resistor. That is not ideal. Okay, so anything in the world is not ideal. Okay, except there is exemption. um, Maximum, all of them, not maximum, 100%, everything, we are trying to become ideal, we are trying to become perfect, but 100% we are not perfect. Okay, there may be knowingly unknowingly many defaults, like that. If we in the filters also we will talk ideal filters, non-ideal filters. Ideal filters, we will expect some type of constant graph. Low pass filter means some type of constant graph, but practically when you do it in the laboratory, we will not get exact sharp cut graph. Okay, there will be a slant, there will be a practical case. Okay, so those are system parameters or non-linearities in the design. And how far the output is affected by the internal system parameters, that is called sensitivity. Sensitivity means how far the system is affected by internal parameters. Okay, manufacturing defect of the device. Now coming to the disturbance rejection, it is reaction to the external disturbances. Okay, how far the error is created due to external disturbances. Sensitivity means how far it is output is affected by the internal disturbances. Okay, parameter, system parameter, non-linearities are internal disturbances, not external disturbances. Now, can a system track the reference input despite of variations in the system? Increased task execution times, device failures, all these are the problems that may be faced. Okay, because of sensitivity issue. If the system is sensitive, it can handle all these 3 points. Okay, it can see the device cannot get failure. It can also execute the task allotted, and then it can also react to the input irrespective of the internal disturbances. There is a system, input is from the input side, internally system is having problem, but the system can react to the changes in the input irrespective of the internal disturbances. Okay, that is the first point. Like that, these are the sensitivity issues of the system. Now, performance specifications guarantee stability, improve transient response. For improving transient response, we should have settling time less, small overshoot. Okay, all this are achieved in the PI controller we discussed. It improves the transient response. PI controller improves the transient response, and PD controller improves the steady state response. Okay, then small steady state error. Yesterday in the controllers we have discussed all this, how to get all this. Okay, in the teaching plan we have the these topics first, then only controllers. So these are the basic things. In order to get these achievements, we are going for controllers. Now, improve robustness with respect to uncertainties. These are the uncertainties: disturbance rejection and low sensitivity. Uncertainty means there is no surety it will happen. It may happen, it may not happen. Okay, but the system should be ready to manage all these issues, ready to handle all these issues. Okay, disturbance rejection means external disturbances for the system. Sensitivity means internal disturbances, anything is there, whether the system is sensitive to that. Low sensitivity means it should not react for the disturbances, internal disturbances. It should be able to handle. Okay, so those are the things. Uncertainty means it is not sure definitely happen, but if at all happens, system should be ready to handle it. Okay, now this is the diagram. Controller we can design using different ways. Root locus method is there, Bode plot method is there. Okay, and only then we will have the open loop transfer function. Output we will check whether it is satisfying the required level. If it is not, how we will check? Based on the performance specifications: rise time, peak time, settling time, gain margin, phase margin. Okay, in time domain, in frequency domain, we will check whether the system is giving the required performance. Otherwise, we have to adjust the controllers, adjust the compensators. Okay, in order to get the desired output. What to adjust? To make the sensitivity low, disturbance rejection for the system to be high. Okay, like that. To improve the steady state response, to improve the transient response, like that we have to target and we have to improve the performance of the system. Okay, these are the things present in the teaching plan. These are the things present in the teaching plan. Stability we have discussed, steady state, transient we have discussed, disturbance, rejection, insensitivity. Robustness means these two parameters, robustness and uncertainty means there is less chance of happening. Robustness means there may be frequent happenings of external disturbance and internal disturbance, like that. So root locus method of feedback control system. So here in the diagram I showed you, there is root locus method, Bode plot method for designing the controllers. Okay, we are not going in depth. There is possibility, that's all what I want to say, because if it is long answer question, we can deal with the design of controller in root locus method, design of controller in Bode plot method. Okay, so as of now, I am giving what are the possibilities.